Okay, so this is an orbital mechanics question involving gravity and two satellites around a planet. So we have a planet in black in the very center, and it has a radius of, it's not Earth, it's just some other planet. It has a radius of 9 times 10 to the 6 meters, and then there's a blue satellite that's orbiting, and it's a circular orbit, and it has a mass of 68 kilograms. It has an orbital radius of 7 times 10 to the 7th meters. So the radius is not the radius of the satellite. It's from the center of its orbit, okay? Or essentially from the center of the Earth. So it's like that. That's its radius because it's orbital radius. So anyway, the blue satellite has a mass of 68 kilograms, has a radius, orbital radius of 7 times 10 to the 7th meters, and it has a velocity, a linear velocity, if you will, of 4,800 meters per second. And then there's another green satellite, and it has a mass of 84 kilograms. It has a radius of 3 times 10 to the 7th meters. And the question is, what's its velocity? So if you remember from before when talking about circular motion, if we imagine there's some sort of like force here in the middle that's moving something, and there's a rope, and then there's like a rock or something, and this rock is moving in a circular pattern like that, right? So you may remember this rock that's moving in a circle. Well, how is it moving in a circle? Well, there's tension. There's a rope, right? And then there's tension in the rope that's pulling it this way. And that tension is causing an acceleration. And the acceleration is called radial acceleration or centripetal acceleration because it's towards the center. So when you're moving things in a circle, there is, as I mentioned, radial acceleration. That's acceleration that's toward a radial or centripetal. So that it's a vector, and it points toward the center of the circle, which is the same, and the tension force is also a vector, and it's also pointing towards the center of the circle. Remember, because forces are vectors, and acceleration is also a vector. But there's also another acceleration vector. It can be the tangential acceleration or a tangential. But that's if you only have tangential acceleration if the speed is changing. So like if this ball that's going in a circle, if the speed of that thing is changing, then you will have tangential acceleration. But in this case here, if the ball is just moving in a circle and it's not changing its speed, the tangential acceleration is 0. And then the only acceleration in that case that it has is just the acceleration towards the center, or radial acceleration, or centripetal acceleration. So acceleration, C for centripetal, or if you can do R for radial, I guess if you want, it's V squared over R. Okay, so if you know the velocity of this ball, for example, in here, if you take it's square, if you square the velocity and then you divide by the radius, then that will tell you the acceleration towards the center. Okay? Now, why is this important? Well, so what you can do, well, the thing is that this satellite here, the satellite system with like this planet in the middle, is really the same thing. And so instead of like a rope swinging a ball in a circle, we have a planet's gravity swinging the acceleration in a circle. Sorry, the planet's gravity swinging the satellite in a circle. Okay, so these two things, even though they look completely different, like, well, maybe not conceptually, but like actually, like a rock on a string versus a satellite or like the moon orbiting around the Earth. Those seem like completely different things, but actually the underlying principles are pretty much the same. So what you could do, though, is you could say, and if you remember from this, is from Newton's second law, right? His second law. Now, what you could do is you could create a force diagram like this, and you could say, okay, here is the ball, or it could be the satellite, whatever is in the center, and then we could map out all the forces on this ball, or planet, or satellite. So if the center is here, I'll do an X right here, is like the center, then the force is going this way, right? Because it's pulling. It's pulling. In one case, it could be the tension of the string, or it could be the force of gravity that's pulling it in. Okay, so the force is going this way. And then the question is well, is there another? Well, in the case of the planet, in the case of the satellite, is there a force going up? No. Is there a force going down? No. Is there a force that's going in this opposite direction? No, there's not. There's only one force. And because there's only one force, you may think, well, there's only one force, so that means that means it has to be accelerating, and it is. It is accelerating. There's radial acceleration. So the reason these forces are in balance is the reason there is the reason there's radial acceleration or acceleration in general is because forces are in balance, right? From Newton's second law is if you have an imbalance of forces, you will have acceleration. And because there is an imbalance of forces, there's a force over here on the left, but there's no force on the right. Okay, so therefore there's going to be there is going to be an acceleration. So from Newton's second law, we could say the sum of the forces. Remember, it's the sum of the forces. In this case here, we'll call this axis the x. We'll call this one the y. You can name your axes like whatever you want, but I'll just call like this, like the back and forth, if you will, like towards the center of the circle and away from the circle. We'll just call that x. Okay, so because when you add up the forces, you have to do them on a particular axis. You have to do them in the x or in the y or the z or whatever axis that you're in. Okay, and so here we're talking about this axis. Okay, we're talking about the x-axis. So the sum of the forces in x, just that axis, is equal to the mass times acceleration. But the acceleration is not normal acceleration; it's centripetal acceleration. So you have to make sure you put a C there because it's not normal acceleration; it's centripetal. So you have to make sure we mention that. Okay, then sum of the forces. Well, there's only one force. It's the force due to gravity. We'll do like a little g there, and it's equal to mass. And the mass of what? Well, in this case here, it's the mass of this. We'll do S for satellite. The mass of the satellite times the acceleration. This is the centripetal acceleration, obviously, of the satellite. Okay. Okay, so it's still Newton's second law. It's still F equals ma. But so now the force is the force of gravity. And this is where this is where you can use the gravitational definition for gravity. So you may remember it's the universal constant g times the mass. There's basically two masses, right? The mass of the satellite times the mass of we'll call it P, the planet, over the radius squared. Okay. The radius of where? The radius between the planet and the satellite. Okay, the radius between the planet and the satellite. So this is Fg, right? This is that force. It's the universal constant g times the mass of the satellite times the mass of the planet over r squared, which is the distance from. It's the radius, right? It's the distance from the planet to the satellite. Is equal to the mass of the satellite times the centripetal acceleration. Okay. Now I'm actually gonna erase this. So I'm gonna replace the centripetal acceleration, remember, with v squared over r. So this becomes v squared over r. So we just replaced this with that. Okay, now we can do some eliminations. So we have the mass. We can remove the mass of the satellite is the same there, and then we have. Oh, I should also mention that this v here is the velocity of the satellite. Right, that's the velocity of the satellite. Okay. So and then. What else you can do is you can multiply everything times r, right? You can multiply this side times r, and you can multiply this side times r. And if you do, then that goes away, and that goes away, and then that goes away. And so then the r, we can move the r over next to the VS, so I could remove the R and put it over here, times R. And so then you end up with gravity times the mass of the planet is equal to V squared R. Okay, great. So remember, we're trying, and then remember that this VS, or the V, is the velocity of the satellite, okay, which is what we're looking for. Now, we're trying to find the velocity of the satellite. That's what we're looking for. So we can solve this equation for V instead. So I can just say the velocity squared is equal to G M P over R. Right? You just move the R under there, and then I can get rid of the 2, get rid of this, right? Get rid of that by squaring that. Okay. So that's the velocity. So in order to find the velocity, remember up here, remember we have this green thing. We need to find its velocity. So in order to find its velocity, well, you would take the G, which is the universal constant, times the mass of the planet over R. R, of course, is the radius of the satellite. It's the radius of the satellite. And then the M is the on top is the mass of the planet. Now, the question is, do I know what the mass of this planet is? No. I was only given R. See that? I was only given R. But I could find the mass of the planet by just up here at the top, this guy here, I could just like rearrange this equation. I could say the mass of the planet is equal to V squared R over G. Right? And so if I do that, then I can plug in the velocity. Oh, so yeah, so in order to do this, I need to know the velocity and the radius of some satellite, and I already know G, right? So do I know that? Yeah, I have the blue in here, right? See, the blue one, everything is given. I have M, I have the mass, I have the radius, I have the velocity, I have everything I need. And so if I plug that in, I can actually get out the mass of the planet. So I'm using the blue satellite to figure out the mass of the planet. And if you do that, you'll end up with essentially like 2.41 times 10 to the 25. This is mass, so it's kilograms. So it's big. So this is the mass of the planet. So all I did is I took this equation here, and I can solve it for V and get the velocity. I can solve it for the mass of the planet and get that. Once you have the mass of the planet, then you can substitute that in right here. You can take this mass and you can substitute it in right here. Oh, sorry, go back. You can substitute it in for this guy right here, mass of the planet. And then you have G, which we know what G is, times the mass of the planet, which we know what that is. And then R, which we know what that is because it was given, which is right here. See, R was given to us. And so now we have everything. And then we do that, and we do the square root of that. And then when you're done with that, you'll end up with the velocity. Let me change it to red. The velocity of the satellite is equal to 7,332 meters per second. Okay. Now, so that's the answer. But I want to show you something interesting. So here, I was trying to find the velocity. I'm gonna take this equation right here, and I'm gonna bring it down. I'm gonna bring it down here. So the velocity is equal to the square root of G times something, mass of the planet, over R. Now this R is the satellite. Okay, so the velocity, it's the velocity of the satellite, and it's the radius of the satellite that we're talking about, okay, in question. And then the G is, of course, the universal the gravitational constant. And then I need to find the mass of the planet. Now, I already had that here, right? This is the mass of the planet, how you find it. And so that is, let me just change its color. It's v squared r times g, right? So, but the velocity here, but because I'm trying to find the mass of the planet, I'm going to use satellite, the other satellite. Maybe call it O, satellite O. So this is O, this is the other satellite, this is the other radius, okay? So O means like the other satellite. So here when I have S means the satellite I'm talking about now, the one I'm looking for. And then O is like the other one. So O for other. Not to be confused. So if you do this, you'll notice that the G's cancel. And then you'll end up with the G's cancel. And then you end up with V squared times R, let's say R0 over RS. Okay. And but this is all underneath the square root symbol. But you can pull out because velocity is squared. You can just pull that out, and you could say velocity. This is the other one. Times the square root of R0 over RS, and that equals the velocity of the satellite. And then yes, And so that's basically it. So what I'm trying to say here is before. Let me do like this green one. Is remember I actually figured out what G was. Sorry, the mass of the planet. Where was it at? Oh, right here. Yeah, that was the mass of the planet. Remember, I had to figure that out. And then I plugged the mass of the planet in. Here, if you would have just continued with the algebra, you realize you actually don't need the mass of the planet. All you actually need is if you continue the derivation. The velocity of the satellite that I'm looking for is actually just equal to the velocity. This is the velocity of the other satellite. The other satellite, the one that I have, times the square root of the radius of the other satellite over the radius of my satellite, the satellite in question. So you don't need, so in this here, I don't even need G. I don't need the mass of the planet. Actually, I don't need any of the masses. So the mass of the planet, the mass of the first satellite, the mass of the second satellite, I don't need any of that stuff. So actually the only thing I need are, really the only thing I need is just the two radiuses and then the velocity. That's it. So yeah, you can solve it like this, but and get the mass of the planet and then kind of backfill it in. But like I said, if you continue the derivation, you realize you actually don't even need G and you don't even need the mass of the planet. So, which is probably a useful exercise to just remember. So like sometimes you don't actually need to like do extra work. And then, yep. So just in recap, and I just want to like drive this point home. The way we solve this is just a normal problem on Earth where you have like a rope and you're trying to swing it around and there's tension in the rope, and this is the same thing except instead of tension you just have the force of gravity. Okay, and we did this diagram here where we have the force going, pulling in this direction. Okay, and this is along the radial. So the x is like the radial axis. Okay, and like back and forth. So remember when you do F equals ma, or when you do F equals ma, you have to do it on each particular axis. Okay, you have to do it on each particular one. And the other tricky thing is that the acceleration is not normal acceleration. This is called centripetal acceleration. So it's not the same as tangential acceleration, because that's different. So the v squared over r is only radial acceleration, okay, which is what we had here. Okay, and anyway, I think that's about it.